Hello and welcome back to the next video on calculus differentiation. In the last video, we have seen how magical the first principle of differentiation is. So today we're going to go through some work examples so that we can do the magic ourselves and get our hands dirty with the first principles of differentiation. But first of all, I would like to explain conceptually what is happening when you apply the first principles, because the most common misconception students have is, are we solving for x? And the answer is no. Let me explain with a picture. Okay, so sometimes you're given a question, right? And the question says, here is a function, in this case it's x squared. Okay, and please find the gradient for me at, say, this 3 points. And the good old way would be to, okay, let's draw a tangent line. And the tricky thing about tangent line is that you can never get it exactly right. Okay, but after you draw the line, you pick 2 points on the line, and then you apply the rise over run formula, y2 minus y1 over x2 minus x1, and you get the gradient at 1 point. Repeat that 2 more times, and you get the gradient at all 3 points. But if you know the first principles of differentiation, we have a much better alternative. And that is, when you apply the first principles, right, what you're doing is you're creating a brand new function, what we call the gradient function. Okay, and what you need to do after that is, okay, let me just write this down. Say this is x1, this is x2, and this is x3. All you need to do is substitute x1, x2, and x3 into your gradient function, and you get the gradient of all those 3 points. Sounds good? Okay, you might also notice that saying applying first principle is kind of a mouthful. Okay, so what are the alternatives? What can we say other than applying first principles? So let's talk about notation. Before I talk about notation, you might notice some similarities if you have taken chemistry. This looks like a chemical reaction. You have your reactants over here, you have your underlying condition that needs to be fulfilled before the reaction happens, and then you have your product on the right hand side. Yes, it looks exactly like that. And that's what we're doing. You put in a function, you apply first principles, and you get a brand new function. Okay, so first of all, other than applying first principles, what can we say? We can say differentiate. Yeah, differentiate. And this one is really familiar because it is the name of our topic, differentiation. Okay, and next, let's say if you started with a function f of x, okay, and say if you differentiate, what do you get on the right hand side? You will get f prime of x. This one I think we already know, we went through a few times. But what if you're given an equation? For example, y equals to x squared, okay? And you apply first principles, for example. What do you get? You actually get this thing called dy over dx, which we just say dy dx for short, okay? So you might know this has a special name. This is what we call the Leibniz notation, and you will know who Leibniz is, yeah, if you watch the first few videos. Leibniz notation. Okay, so one thing I need to be very clear over here is this is actually semantics. Okay, so if you start with f of x, you wouldn't end up with dy dx. You actually write f prime. Okay, likewise for y, if you started with y, you don't go to f prime, you actually get dy dx. So be very clear what you start with and what you end up with. Okay, and last of all, I'd like to just add one more thing, and that is we have a collective term for the things on the right hand side, the products, right? We call them derivatives. Okay, because the right hand side is derived from the left hand side. The right hand side would not exist if you did not have an original function or an original equation. It came from there. They're derived there, they're called derivatives. Okay, and with that, I think we're ready to do 2 out of the 7 questions in this worksheet. Okay, so I'm just going to go through 2 of the questions to guide you along, and then after that, maybe you can try the rest of the questions on your own. So let's look at question number 1. It says, given a function negative x squared, determine f prime of x, determine the derivative using first principles, using differentiation. So I think it's good for a start to write this down. Tell the examiner what you're doing. Tell them, oh, I'm going to use the first principle of differentiation, and then write down what exactly is the first principle. Because you're new to this topic, we are new to this topic, we are doing it for the first time, it's good to write down the formula a few times to get ourselves familiarized. Next, you probably want to know, okay, well, what's next? You need to write down what is f of x plus h. Okay, so what is f of x plus h? Here's a quick revision on functions. So functions work this way. Okay, if you have this f of x equals to x squared, it means that you are substituting the value of x and you're getting x squared. Okay, and if you substitute the value of a, then you'll be getting a squared. Then it goes without saying that if you substitute x plus h, you're going to get x plus h all squared. Okay, and we know x plus h is actually equals to x squared plus 2xh plus h squared. Now, one thing to remember about this question is we are not dealing with x squared, we are dealing with negative x squared. So all these come with a negative sign. Okay, so this is going to be negative x squared, negative 2xh, negative h squared. And that's what I'm going to write for my f of x plus h over here. So in the next line, f of x plus h, negative x squared, negative 2xh, negative h squared. Okay, not to forget, I still have a negative f of x, which should just be negative x squared. That is actually a positive x squared. And all of this is divided by h. Okay, and now that we have fully expanded, fully laid out all the terms in the numerator, it's time to simplify. You might notice that, hey, this is a negative x squared, this is a positive x squared. Together, they become 0. We can leave that out. So in the next line, what we have left are the remaining terms. Okay, and in the remaining terms, we have something really nice and convenient. That is, we can divide throughout the numerator and denominator by h. So divide by h, and then what I'm left with, I got no more denominator, it's just this. Okay, and here's where we ask ourselves the question, what happens to this negative 2x, negative h, when h becomes smaller and smaller, like 0.00000001? Well, effectively, it becomes so small, it's negligible. So when it's negligible, we like to write something like this, like it goes towards 0, it's almost 0, right? And we can just pretend it does not exist. We can ignore it, okay? And that's why we say, hey, after applying first principles, my gradient function is negative 2x. Okay, yeah, so that was the first question. Now let's look at another example. Okay, in this second example, we are dealing with a new function. This function is negative 2x squared plus 3x plus 1. We want to find the derivative, which means we want to find f prime of x using first principles, using differentiation. So again, I think it's good to write this down. You're going to use the first principle and then write down the formula in the first step. And then next you want to ask yourself, what is f of x plus h? Again, to help you out, okay? Since f of x is this, meaning that if I substitute x, I'm going to get negative 2x squared plus 3x plus 1. Then f of x plus h is just replacing all the x's with x plus h. Then you have negative 2x plus h all squared plus 3x plus h plus 1. So 1 is a constant term. It does not have x in it, so it is still 1. So that's what I'm going to write in the numerator for f of x plus h. So negative 2x plus h all squared, plus 3x plus h plus 1. Okay, and not to forget we have a negative f of x. Okay, we just need to copy this down, but put a negative and a bracket in front of it. And all of this is divided by h. Alright, the next step will be to expand the brackets, starting with this one first. Yeah, so we know this is an identity, x squared plus 2xh plus h squared, but we're going to multiply it with negative 2. So that's going to give me negative 2x squared, negative 4xh, and negative 2h squared. Alright, and the next bracket is this one. We're just going to multiply by 3. So that one is quite straightforward. And don't forget the plus 1. Okay, next we're going to take this negative sign and multiply it into every single term inside here. They'll give us a positive 2x squared, and the rest of the terms are negative. And all of this is divided by h. Now we have fully expanded out the numerator, it is time to simplify. And we can cancel out these terms. Negative 2x squared can be cancelled with positive 2x squared. Positive 3x with negative 3x, positive 1 with negative 1. Now, a rule of thumb is that we are always looking to cancel away every single term in our f of x. Okay, that's how I know what to cancel away very quickly. All right, so the remaining terms are here in the next line. These are the remaining terms. Okay, and you realize another thing is that, hey, we can divide throughout by h. Divide by 1h throughout, and then we have no more denominator. We are left with this. And then you ask yourself again, what happens when h becomes really, really small? Then you say that, oh, it becomes negligible, it is almost 0, and we can treat it as 0 if we take limits. Yeah. So what we are left with is negative 4x plus 3. And this is our gradient function. This is our derivative. This is f prime of x. Okay. So I hope these 2 work examples has helped you to understand what we are doing over here. There are 5 more questions at the back of this worksheet. So I hope you can go through them and try it for yourself. Okay. And I'll be making a video, or maybe I'll be posting the solutions to these 5 questions at the back online. Okay, so I come to the end of the video. Thank you for watching. I hope to see you in the next video. Until then, catch you on the flip-flop.